everyone. So today is the first day of our notes for the scientific method. Hooray! So basically what we're going to be doing today is learning a little bit about the scientific method in preparation for one more lab that we're going to have before the end of school. So before we can do the lab, we need to know a little bit more about the scientific method. Generally, it seems that some of you may have heard about the scientific method, you may have remembered some of the steps, but you didn't really go into it too much in detail yet. So we're going to do that in this presentation. This is going to span today and then on Monday of next week. And then we're going to go right back into our experiment, which will wrap up forces in motion for us. So let's get right into it. We have the scientific method. And basically, scientific method is a process for experimentation that is used to explore observations and answer questions. So pretty much it's the official method that scientists use to rule out or to single or narrow down a possible answer to a question. Now, when we think of the scientific method, we often think that it's just for scientists and scientists are the only people who use it. But that's really incorrect. Honestly, the scientific method is just putting fancy names to problem-solving techniques that we use as humans every single day. So I'm going to give you an example. And the next slide, we would normally watch it in class if we were there. I know it's a scary spider video, sorry. But it's actually a really good video for you to watch on your own time. It shows how the scientific method is not linear. You don't have to follow it in just, step 1, step 2, step 3, step 4. It's part of the scientific process. So that kind of goes over, do we need to follow it exactly? No. So in your own time, this is actually a pretty cool video to show how a new species of spider was found in caves of Oregon. So they kind of went through, they weren't sure if it was a new species. They followed the scientific method, but they ended up going back and forth and back and forth and back and forth to make their final determination. So I want to go over how we use the scientific method in everyday life. And honestly, you probably use the scientific method while you were doing your egg drop project. So these are the official steps of the scientific method, but again, they don't have to be in that exact order. So let's say you have a problem, and perhaps this has happened to you yesterday with our crazy storm, but let's say you go into your room and you realize you try and turn on the light. You come home from like a softball practice. Imagine before coronavirus, softball practice or soccer practice, baseball practice, dance class, whatever nightly activity you do. You go home, you go to your room, you turn on the light, and nothing happens. Okay, you may ask yourself, what the heck? Why isn't my light turning on? That's a question that you may have. From there, you're going to gather information. You may think back, wait a second, I just walked through my whole house and all of the lights were on in my house. That was gathering information. You may come up with a hypothesis, okay? If there are lights on in the rest of my house, but it's just my room that's not lighting up when I flip the switch, maybe, and this could be your hypothesis, maybe my light bulb is out. You can conduct an experiment. How would you conduct an experiment? You'd go and get a new light bulb, twist it in, turn on the light, and see if it works. You end up doing that, and you see that no, it did not light up. So you analyze your results. It's not my light bulb. What else could be a potential reason for my lamp or my light not turning on? You may go back to the drawing board, gathering information. Let me think back. I did turn my fan on the other day because it was hot. Maybe I pulled the wrong string. If you have, a ceiling fan and a light attached, maybe I pulled the wrong string and I actually turned off the light. So that may become your new hypothesis. I need to pull the lamp string and maybe it'll turn on. You conduct your experiment, you pull on it, and you analyze the results. Hey, you can see now. Great. You share your results. Woohoo, I got it, Mom. Here's the extra light bulb that I don't end up actually needing. Ta-da! You've just gone through the scientific method without even knowing it. And this happens a bunch of different times a day, way more often than we even realize. Because honestly, like I said before, it's just a problem-solving method that we use intrinsically as humans. So we're going to go into each of the separate steps today. There is a lot of new information. So today is going to be information, and then Monday is going to be kind of using it in practice. Okay, so we're going to do a lot of examples on Monday. Okay, so first step is to ask a question, or really to make an observation. Sometimes you'll realize that these steps have different names, but they're talking about the same general thing. So if you were to Google steps of the scientific method, one may say ask questions, one may say make observations. Same thing, just different words. So basically during this step, you are looking at observations you've made, any facts that you've found, and you are identifying questions that you may have about a topic. Okay, so some of these things could be, for example, why is my light not turning on? Why does my heart beat faster on hot days? How come hair gets darker when it's wet? Why does my dog tilt his head when I talk to him? These are all examples of possible questions that you may ask that you want to figure out. Okay, that's the first step, is to be curious. Second step is to gather information. So, like I said with our example of the light bulb, you may peek out into the other room, see if their lights are turning on. You may look across the street, see if their lights are on. You may Google something. Pretty much you're doing some research on the topic to see if someone has already answered your question. There's no point in doing, an experiment if you can just Google the answer and see it really, really easily. I mean, obviously some experiments are fun, let's do them, but it may save you some trouble. So if you can't find an answer, doing some research may help you narrow your focus or kind of give you better information to then do your experiment with. Okay? So that's kind of the second step. So asking questions, gathering information, or doing research. Third step is to write a hypothesis. So when we hear the word hypothesis, sometimes we think, oh, wow, this is really tough. It's going to be a real hard science thing. We're going to keep it simple, okay? Basically, it's an educated guess or a prediction about a problem, and it has to be testable. Now, that's kind of a fancy catch that you'll get on to later on when you learn about science in middle school and high school. But for now, we just need to know that it is a prediction or a guess about what's going to happen. It's sometimes seen as a possible explanation to the question or the problem. And there's a very particular way that we're going to be writing these. We'll see that in a little bit. Basically, the whole purpose for this hypothesis is that eventually evidence that you collect will either support or reject your hypothesis. So we don't say, hey, I was right, my guess was right, or oh, my guess was wrong. We say my hypothesis was supported or my hypothesis was rejected. Those are the scientific terms that we use to reference our hypothesis. Okay, so this is the special format that we have to use when we're writing our hypotheses. It's an if-then format. And once we get into our experiment or our example on Monday, we'll go over more examples of these types of hypothesis. But basically, we are having, if I do something, then this will happen. If I do something, then this will happen. So here is the if. If a flower receives light from a fluorescent bulb, an incandescent bulb, and the sun, then the flower under the sun will grow the tallest. If I do this thing, basically if I put a flower underneath a fluorescent bulb, an incandescent bulb, and the sun, then the flower under the sun will grow the tallest. Then I think this is what will happen. So I want to show you an example of these because we're going to be using this example more so as we move forward with these notes. So I want to show you kind of what each of these light bulbs are. So this is a fluorescent bulb. It's that curly Q kind of deal. Inside of it, it has gas, and when electricity flows through it, gives it more energy. And that gas, a property of that gas is that when it has more energy, it illuminates. So that's how it creates light. That's a fluorescent bulb. Over here, we have an incandescent bulb. And basically, if you look over here, these kind of like the old school light bulbs. We have a little metal filament inside of the bulb. And when electricity flows through, the little filament conducts electricity, gets very hot, gains energy, and it glows. That's how it creates its light. And the sun, obviously. Ta-da, here's the sun. Okay, so if we were to put flowers under this type of bulb, under this type of bulb, or the sun, this person who came up with our hypothesis thinks that the flower under the sun will grow the tallest. If you look, they're giving us real clear examples of what they're doing. They're putting light from a fluorescent bulb and incandescent bulb on the sun. Then the flower under the sun will grow the tallest. They're giving us very clear predictions of what will happen. That will come in handy later on. But again, basically, big takeaway for hypothesis is that it's a prediction on what you think will happen, depending upon what you do in your experiment. All right, so that's our hypothesis. Now, conducting the experiment is going to be the hardest part. Not actually doing the experiment. It's actually all about the planning. So at this point, everyone wants to just jump in and start doing the experiment. We can't yet. There's so much more that needs to be done to plan things out. And we're going to take a look at that now. Okay, so we've asked questions. We have done some research or gathered information. We've come up with our hypothesis, what we think will happen when we do this. Now it's time to plan our experiment. So we need to design a controlled experiment. And basically what this means is that we're only working with one variable at a time. So think about what could be an issue if we were to change more than one variable at a time. So I'm going to go back to that diagram of our different light bulbs or light sources, I guess you could say. And we're putting a flower underneath each of them. Great, lovely. What would you say if I said, okay, well, they're under different light sources, and now the fluorescent bulb, the plant underneath the fluorescent bulb is going to be watered every day. The plant underneath the incandescent bulb is going to be watered every other day. And the plant underneath the sun is just going to be watered whenever it rains. Now, we're actually changing two things. We're changing the type of light and how much the plant gets watered. So when we make our measurements at the end and we see how well these plants grow, is there any way to know if it's because they grew based upon the light source or how they grew based upon the water? We don't know which caused the difference. So in creating a controlled experiment, we are only changing one thing at a time. If we change two things, I don't know what's actually causing the outcome. So we can only change one thing at a time in a controlled experiment. So that's what we mean by a controlled experiment. We're only changing one thing at a time. And by the way, a variable is just literally a thing that you can change. It's just a fancy scientific term for a thing that you can change. So changing the temperature, changing the type of light, changing the time that it gets light, changing the amount of water that it gets, All of these are examples of variables, and if we change more than one of these, that could have a pretty big impact on our plant. So we can only change one thing at a time. Okay, so that's the first thing when we're planning. Only change one thing at a time. Got it. Next up, we have independent and dependent variables. And this is where it gets kind of dicey. We need to think about, what are we going to be changing on purpose in our experiment, and what's going to happen as a result? So what are we changing on purpose? What's going to happen as a result? Okay, so an independent variable is the variable that the scientist is deliberately changing. What is the scientist actually saying? You know what? I'm going to do this. Whatever you came up with in your hypothesis, what you're going to do, that is your independent variable. So for this scenario, if a flower receives light from a fluorescent bulb, incandescent bulb, and the sun, what are we changing in this experiment? Well, if we go back over here, what are we changing? We're changing the type of light they're receiving, aren't we? We're saying, you know what, this is going to get a fluorescent bulb, this is going to get an incandescent bulb, and this is going to get the sun. Interesting. So we are going to say light, but we are not just changing the light, right? We are changing the type of light, because if I just say light, I may be thinking, oh, we're changing the time of light. This guy gets 3 hours, this guy gets 2 hours, this guy gets 1 hour. We need to be specific with our independent and dependent variables. So we are changing the type of light. We're saying you get a fluorescent bulb, you get an incandescent bulb, and you get the sun. Okay? So that's our independent variable. It's what we're deliberately changing. We're saying, wouldn't it be cool if we did this? That would be our independent variable. In the case of our flowers, it's putting them under different types of light sources. Our dependent variable is what's next. That's what we are going to see. Well, if we put them underneath the different light sources, what do we think is going to happen? And again, if we go back to our hypothesis, if we put them under different light sources, then the flower under the sun will grow the tallest. That is our dependent variable. We're looking at what's going to happen if we do our crazy experiment. How do we think it's going to be affected at the end? So the dependent variable is the variable that is observed during the experiment. It's the data that we collect, and it's the result of changing the independent variable. So again, if we're thinking back to our plants, we're trying to see if we change the type of light, how is it going to affect the plant's height? Okay, how is it going to affect the way that they grow? So if we think, how do they grow? Well, how will I know how they grow? What can I do to assess whether or not a plant grew well? Well, I can measure the height. So your dependent variable is the height of the plant. Okay? All right. So that's our independent variable and our dependent variable. Real quick before we get into the last little bit, we're going to go over, we're going to watch a short little video. So here we go. Make sure it's loud.
The scientific method is about ordinary people doing ordinary things. That includes you, me, and other scientists in the world. The scientific method is just a process or steps taken to produce reliable results to answer a specific question. Maybe you think you don't use the scientific method in your life, but I can guarantee that you do. For example, imagine you wake up on a Saturday and you couldn't find your cell phone. That's an observation. Then you do a little research by thinking about the last time you had it. You suspect that it might be in the pocket of your pants from yesterday. That's a hypothesis. And when you check your pants, you're doing an experiment. But science and life don't always go as planned, and you find no cell phone in your pants pocket. So the second observation leads you to think again and recall what else you did yesterday. You remember that you put your cell phone in your backpack during school. So you decide it must be there, and you go and check. And lo, there it is. Life can continue, and you're so happy that you share the results with your best friend and explain why it took you so long to text them back. Science. These are the steps of the scientific method. And at any step, you can go back and repeat the process. Typically, after you conduct an experiment and conclude that your results aren't answering the question, you go back and try something else. And really, truly, observations and research are going on the entire time. Science is a continually ongoing process. Now let's break down each of these steps into their component parts. All that can be observed with the 5 senses are included in observations. You use your sense of smell, sight, taste, touch, and hearing to make your observations in science. Research is an important step in science because it may answer other questions you have and help refine your experiment before you go down a path that leads to nowhere or conduct an experiment that's already been done. Make sure you use reliable sources to learn background information. Scientific journals and online sources that are vetted and trusted are best. Avoid information from blogs and out-of-date textbooks, as the information might not be reliable. Once you have your research completed, you can form your hypothesis, which is a prediction of what you believe will occur. It is often seen as an if-then statement and is very specific. Here's an example. If gummy bears are placed in water for 24 hours, then they will swell to over twice their original size. It has an if and a then, and uses specific terms that make this experiment repeatable. The experiment itself is made of several parts. Most experiments collect 2 types of data, qualitative and quantitative.
Okay, so we're going to pause here for a second. Actually, I'll go over real quick. So basically, we're going to talk about this in a little bit, qualitative and quantitative data. But either way, she'll go over it.
Qualitative data relies on descriptions like soft, yellow, shiny, or wet. Quantitative data relies on numbers like 25 centimeters or 2.3 grams. Once you know what types of data you're going to collect, you can define the variables in your experiment. There is the independent variable, which is the thing you change to see how it affects your dependent variable, which is the thing you measure. So in the gummy bear example, the change in the experiment is that the gummy bears are being placed in water. The dependent variable is the volume of the gummy bear, which is measured before and after it's soaked in the water. A valid experiment.
Okay, so that is a little bit more on independent and dependent variables. So now, once we have figured out what our independent variable is and our dependent variable, now we're going to talk about 2 more aspects, I know this is a lot, of our experiment, which is our 2 different groups. We have an experimental group and a control group. So, an experimental group is the group in which the variable is changed. So this is a literal group, like, okay, half is getting this, half gets that. Just like we separate you guys into groups for projects and different activities in school, we're talking about a literal group. So it's a group that gets the experiment done to them, okay? So if we're thinking of our little light bulb scenario, which groups are getting experimented on? Are we saying that it's going to be the flowers that are under the sun? Is that like a crazy experiment? Not really. That's kind of like normal, right? So any flowers that are going to be put underneath the light bulbs are kind of out of the ordinary. So we would say that's our experimental group. That would be flowers under the fluorescent and incandescent light bulbs. Okay, that's the experimental group because they're the ones that are getting experimented on. It's kind of like a, I wonder what will happen if this occurs. So that's our experimental group. Now, if we go back to the next type of group, we can see that we have the control group. And basically, we think of the control group as a comparison. It is almost like the normal, okay? It's the group that gets no change when we compare it to the experimental group. So whatever is the normal for the type of light, or however you store gummy bears, that's our control group, whatever the normal is. So again, if we think back to our plant example, our control group is going to be flowers that are under whatever normal is. So if you think about how plants normally grow, they grow under the sun. So flowers under the sun. Ta-da, done. Okay, so we are almost done with planning our experiment, but we have just one more thing left, and that's going to be constants. So before we finish up our video, we're going to do this. Okay, so we have our experimental group, the groups that are getting experimented on, our control group, whatever is the normal. We'll kind of use it as a comparison, because how would we know if the plants are growing funky if, that's how they normally grow? Now we have our constants, and basically what we have here are variables that have to stay the same. Okay, certain things that must be the same between the experimental group and the control group. Okay, we call them constants. And if we don't keep them the same, they're going to mess up our answers or our outcome. So basically, this kind of goes back to thinking about a controlled experiment. Think back to when I said, all right, we're going to give this guy water every day. This one is getting watered every other day. And then the sun gets watered whenever it rains. Okay? That would be an issue because it would create an uncontrolled experiment. So we would think, all right, well, we definitely want to keep the amount of water that each of the plants get the same, because we're only changing the type of light. So that would actually be an example of a constant amount of water. That has to be the same for our experimental groups and our control group. Okay, so I'm going to actually put here, this is an experimental group, control group. Okay, so things that have to be the same between all three of these is it has to be the same amount of water. Okay, think about what other things could mess up our experiment. What if we use different types of soil and we planted the ones underneath the light bulbs in potting soil and the one underneath the sun and just whatever dirt's outside? Well, potting soil has fertilizers and other nutrients that plants need. So that could actually have an effect on our experiment in addition to the light. So that would be a constant, something that has to be kept the same so our experiment doesn't get messed up. So type of soil. The temperature that they're in has to be kept the same. Okay, we can't have these two in refrigerators and then this one just out in nature. That could make a difference on how a plant grows. Amount of water, type of soil, temperature. We can say time exposed to light. Okay, if this guy only gets 5 minutes a day with the light on, that's going to have an impact on how it grows. So these are just some examples of constants. If you really went crazy, you could come up with thousands of different examples. The air percentages have to be the same for each group. Again, it's as crazy as you want to make it, but it needs to be anything that should be kept the same between both groups, the experimental group and the constant group. Pretty much all of your groups has to be the same so that you have a controlled experiment. Okay, so that is our lovely conducting an experiment. After we've done all of those steps, now we could finally actually do the experiment, but we need to plan them out first. So we're going to finish up this video. It'll wrap up that last little bit, And then we have just a few more slides.
We'll have both an experimental group, where the independent variable is altered, and a control group, which can be used to compare the experimental group to the normal or unaltered version. In the gummy bear experiment, the bears placed in water are the experimental group, and the dry gummy bears are the control, because that's how gummy bears normally are. So to summarize, an experiment should have an experimental group and a control group. The experimental group will have an independent variable and a dependent variable, and the data that is measured and collected can be qualitative, quantitative, or both. Thanks for watching this episode of Teacher Sped. Don't forget to like and
Okay, so let's go back to our notes. Okay, so like she mentioned, once we actually do the experiment, we gather our data, we want to look at it, okay? Because why would you gather data and then just not do anything with it? That would be silly. So we are going to analyze our results. And basically, and let me make this a little bit clearer. When we are, that's peculiar. I have to unbold it, I think. This font is something funky where it will, if it's bolded, it makes it like a cartoon letter for some reason. Okay, so for looking at our data, we do have two types of data that we could be looking at. Qualitative data is data relating to the quality of something. It usually uses descriptive adjectives, and I like to think of it because it has an L, and I think of like ELA, language, literacy. Those are using words. So qualitative data is information that you collect that's a description. It went fast. It looked healthy. It was green. Anything that you can describe using an adjective, that would be qualitative data. Quantitative data is data relating to numbers, measurements. It is 5 inches tall. It went 3 miles an hour. The temperature of the planter or pot was 70 degrees Fahrenheit. Those are all quantitative data markers and measurements. So qualitative is something that usually relates to words, uses descriptions, adjectives. Quantitative data is relating to numbers. Okay, so when you are looking at your data, especially the quantitative data, it may be helpful for you to actually graph it to fully understand it. We'll see this when we do our experiment, but graphing the data sometimes allows you to see certain trends that you wouldn't see, or patterns in the data. That's kind of interesting. It could even lead you to more questions. Okay, and then finally, you would share your results, okay? That's kind of our woohoo, hooray step that we have at the end. That's just nice. That's kind of you turning in your work to me. Okay, so we finished all of this information. I know, it's a lot. On Monday, we are going to be going over the practice example. So we're going to be taking all of this information and putting it together with one unified example, okay? So for today, all you need to do is fill out the exit pass for today, which is pretty much just going over what an independent variable is, what a dependent variable is, constants, experimental group, control group, that sort of thing, okay? The scientific method example will be up for you on Classroom so you can look at it. But the definitions are in the notes for you, okay? So if you need a definition of what each of these things are, that would be in the notes right here. So for today, again, we're just doing the exit pass. Monday, we'll do an example, and then this is all in preparation for our final experiment on forces of motion. So if you have any questions, you can always type in a private comment on your assignment. But other than that, I hope you guys have a lovely day.